Okay, so good evening, everyone. Uh, my name is Avik Mukhopadhyay, and I welcome you to the final and 12th live session of Signals and Systems. And today we will be looking at some problems uh, based on Z transform and its properties. Okay, so it's very similar to the previous transforms that you have seen so far, such as the Fourier transform, Laplace transform, but today will be confined to the Z domain. Okay, so through the examples, I'll be trying to review the um, some of the properties, important points regarding Z transform and also the region of convergence or ROC, right? Okay. Okay. So let's begin with the first question. Okay, my mic is on. Fine. Okay. All right. So here is the first question. So we are asked that for the Z transform of a discrete time signal given in equation 1, so here is equation 1, where you are given the Z transform of a discrete time signal. So the Z transform is denoted by capital X of Z, okay, and it has this expression. So it's the commonly encountered form in the rational form, as you can see, where in the numerator you have a polynomial in Z, it's a first order polynomial, and in denominator you have a second order polynomial, which is actually nicely factorized into two first order polynomials. So for this given Z transform, which of the following options cannot be a valid region of convergence or valid ROC? Okay, that you have to decide. Okay, so for this we must know what is a valid ROC. Okay, so let's start. Okay, so what is valid ROC? Okay, or which stands for, as you know, region of convergence. Okay, the key point that you should remember is that we have seen this in the lectures that the ROC should not contain any poles. Okay, so what are poles? The poles are basically the roots of the denominator polynomial of your Z transform, right? For example, in our question, as you can see in our question, x of z has this form. So the denominator is the product of these two terms, right? Z plus 4 and z minus 3. So the roots of the denominator polynomial will give you the pole locations. Okay, and similarly the roots of the numerator polynomial here, which is at z equals to 2, will give you the 0 location. Okay, so these are zeros and poles definition. So we have seen this before also. So now the condition for a ROC to be valid is that it should not contain any poles. Okay, the poles should not lie within the region of convergence. Okay, so let me write that. So ROC should not, okay, should not contain any poles. When I say should not contain any poles, I do not discard the fact that they can be bounded by poles. So in general, the ROCs are bounded by the poles. Okay, so the poles will govern the boundary of the ROC. Okay, and however, it should not lie within the ROC. So that is the main point. Okay, so I'll write in bracket also that the ROC may be bounded by poles. That is allowed. And in our question, the given Z transform x of z is z minus 2 divided by z minus 2, sorry, z minus 2 divided by z plus 4 into z minus 3. This is the form. So clearly, if I ask you what are the pole locations, okay, I'm not really much concerned about the 0 location, although there is one 0 present at z equals to 2, but we are not much concerned about it. So I'll only focus on the poles. So the poles, where are the poles located here? If you find the root of the denominator polynomial, basically at z equals to minus 4 and z equals to plus 3. Right? And how do we represent the pole 0 plot? So basically there are two perpendicular axes. One is the horizontal axis, which is the real part of the z. So here z is a complex number, right? And the vertical axis would be the imaginary part of z. Okay, it's the imaginary axis. So sometimes you will find this kind of a notation with sigma being the real part, the real axis, and j omega as the imaginary axis. So this kind of notation sometimes is used. Also sometimes, like you will see this kind of notation: real part of z, like real part of z, re of z, and imaginary part of z, im of z. So that's the real part and the imaginary part. Okay, okay, now let's plot these poles, okay, on this basically on this z domain. Okay, so this is the z domain. We are in the z plane. Okay, so we have two poles, one at z equals to minus 4, let's say somewhere here, another pole at z equals to plus 3, let's say somewhere here. Okay, so they are denoted by this cross marks, and we use some circles to denote zeros. Okay, so I'm not plotting the 0, you can plot it. So there will be 1 0 at z equals to 2 like this, but let's not go into that. So yeah, now we have to decide which of the given ROCs in the options cannot be a valid ROC. So let's check it option by option. Okay, so the first option is mod of z greater than 4, mod of z greater than 4. So case A, okay, case A is saying mod z greater than 4. What does that mean? Mod of z greater than 4, it means that z is either less than minus 4 or z is greater than plus 4. Okay, or in terms of intervals, you can also denote it like this: z belongs to the interval minus infinity to minus 4 open union plus 4 to plus infinity open interval, these two. Okay, the union of these two intervals. So if this is my ROC, let's say if this is a valid ROC, so how should the ROC look like if I plot it in the z plane? So basically one region would be from minus infinity to minus 4. So there is one boundary at z equals to minus 4 clearly. Okay, and another boundary is at z equals to plus 4. So let's say somewhere here. This is plus 4. Okay, and the ROC will look like this. So it is less than minus 4. So it's like this. Like this, and so on. And similarly z is greater than 4 also, so to the right of this point. So these shaded lines, these actually extend all the way to plus infinity on the positive side as well as minus infinity on the negative side. Okay, something like this. So this shaded region is my ROC. Okay, so now my question is this, can this be a valid ROC? Okay, what is the condition of the valid ROC? It should not contain any poles, may be bounded by poles, but it should not contain any poles. So let's look here. So from the shaded region, the ROC, looking at the ROC, we can clearly say that the ROC is not containing any pole inside it, within it, right? There is one pole which is at z equals to minus 4, which is lying at the boundary of the ROC, but that is allowed, that is fine. And this pole at z equals to 3 lies outside the ROC. Okay, so that is also fine. So this indeed can be a valid ROC, no problem about this one. So the takeaway is that here the ROC does not contain poles. So possible ROC, right? This can be a possible ROC. So we cannot mark option A to be the invalid ROC. So let us now check the second case, which is case B, the option B. Option B is saying mod z lying between plus 3 and plus 4. Okay, so this is the next option. So we have to check whether this is valid or not. We will again follow the same rule. Okay, now mod z lying between plus 3 and plus 4 means that either z is bounded between plus 3 and plus 4, or z is bounded between -4 and -3, right? And in terms of interval also you can actually express this as z belongs to the interval -4 to -3 union +3 to +4, like this. And again, now we shall plot the ROC. Real part of z, imaginary z, and okay, so we had a pole at -4 and we also had another pole at +3, and now let's draw the ROC as well. For that we also need to have these 2 points as well, here at one at -3, another at +4. Okay, these will be my boundaries of the ROC. Okay, so it will look kind of like this. Someone wants to join. So this is the portion of the ROC on the negative side, and similarly on the positive side we have this shaded region like this. So this is my ROC and this is also my ROC. Okay, and again we need to perform this check whether this is valid or not. So here also you can see that the poles are lying at the boundary of the ROCs. None of the poles are contained within the ROC. So this is also a possible, valid ROC. So the point is ROC does not contain any poles, which means that possible ROC. Okay, can be a possible ROC. So again we cannot discard option B as well. So now let us move to the third option, which is case C. The case C is given by this region, which is mod z less than 2. Okay, mod z is less than 2, which means z is bounded within this region, within this interval. Okay, from -2 to +2. Okay, so we had a pole at -4, at +3, and now the region is within -2 to +2. So it's like this. And again, from the ROC, we can say that the poles are in fact lying outside the ROC. None of them are located inside the ROC. So this is also a possible ROC. So option C can also be in fact a possible ROC. So which automatically by now you can tell that it surely has to be option D, right? Which is the invalid ROC, because there are only 4 options. But still we are going to check it anyways. So let's do that. So look at what was option D. So mod Z between 2 and plus 4. So this is the given region. So we have either Z lying from 2 to 4 or between -4 to -2, and alternately you can also denote this as this union of two intervals. Correct. Let's plot it in the Z plane. Real part of Z, the imaginary axis, imaginary part of Z. Okay. Initially we had the poles here, one at +3, another at -4. So now we shall plot the ROC, which is okay. We need these points as well. So let's say -2 is somewhere here and +2 is somewhere here. Okay. So one of the region is, a portion of the ROC is bounded within these 2 points. Okay, it's like this. Okay, and another portion of the ROC on the positive side is from 2 to 4. So 4 is, let's say, somewhere here. Okay, so 2 to 4 means like this. Okay, so this is my ROC shaded region. So now as you can see that okay, -4, the pole at -4 is at the boundary of ROC, which is okay, allowed, but the pole at z equals to 3 is present inside the ROC, it is contained within the ROC. So this is the problem here. So this pole here the ROC contains a pole. Okay, so which is not possible, right? Okay, therefore invalid ROC. This particular option which says mod z lying between +2 and +4 is an invalid region of convergence because it includes a pole, okay, which is not possible. Okay, so we can say that the correct answer is option D. Okay, right? Okay, now let's move to the next one. Okay, in question 2 we have uh, so it says that if the z transform of a discrete time signal x of n is capital X of z, then the z transform of x of minus n is given by which of the following options? Okay, so I hope already the properties of Z transform has been discussed in the lectures. So this will be like a review of that. So this is one of the properties of Z transform which should be familiar to you. Particularly this is the time reversal property of Z transform. And we have looked at the time reversal property before as well in the context of the other transforms like the Fourier transform, Laplace transform and so on. So let's see if your discrete time domain signal, which is x of n, is reversed in the time domain. So x of n is changed to x of minus n, then what is the corresponding change that happens in the z domain? Okay, so that is what we need to figure out. Okay, so as per the notation, we have x of n, which is the discrete time signal or sequence, okay, in time domain. Let's say it has a z transform given by x of z, capital X of z. Okay, so this script z means z transform. Okay, so this is like z transform, or I mean it's just, you know, yeah, it means that if you take the z transform of x of n, you get capital X of z, and if you take the inverse z transform of capital X of z, you go back to small x of n. Okay, that's the main meaning of the notation. And let's say its ROC is somewhere, you know, it's a bounded ROC, something like mod z lying between small r1 to small r2, let's say. Okay, so of course small r1 r2 are some non-negative numbers, let's say, with r2 being greater than r1. Okay, so our question says that what will be the z transform of x of minus n. Okay, so before that, what is the formula of x of z? So x of z is given by summation n running from minus infinity to plus infinity small x of n into z to the power minus n. Okay. Now let us find out the z transform of our modified signal, which is x of minus n. So z transform of x of minus n is equal to, so this notation is like z transform of x of minus n. So that is given by summation n running from minus infinity to plus infinity. Here my signal is x of minus n, right? This. Okay. Now in order to relate this with the original Z transform capital X of Z, we need to make some substitutions, right? We have to uh, match those forms somehow. So here the natural substitution that we are going to make is, let some other variable, let's say small m, be equal to minus n. Okay, so let m equals to minus n. Now we have to accordingly adjust the upper and lower limits of summation as well. So initially n was the variable which was lying between minus infinity and plus infinity. Okay, now small m is our new variable which is minus n. So initially n was running from minus infinity to plus infinity. Now since we are just changing the signs, doesn't really matter much. So m is running from plus infinity to minus infinity. Okay, like this. So this becomes m summation m equals to plus infinity to minus infinity x of m times z power minus n I can replace by small m. Okay, and this I can rewrite as, okay, now I can rewrite this as, okay, the summation is going from m equals to infinity to minus infinity, right? So I can really exchange the upper and lower limits because it won't change the result, right? Because it's a discrete sum and it's running all the way from plus infinity to minus infinity. So no, doesn't matter if you are going from the positive side to negative side of infinity or vice versa, both are same. Okay, so I'm exchanging the upper and lower limits and I have x of m times, so I can write this term as z power m as z inverse whole to the power minus m. Okay, so I'm writing z to the power m as z to the power minus 1 whole to the power minus m. Okay, and now the last step is I will just replace this variable m by our original variable which is small n. Okay, it's just a change of variable, that's it. Okay, fine. Now we have this form. So okay, what did I do here? By changing variable from m to n. This is what I did here. Okay, now look at this form we arrived at. So this is exactly the form of the Z transform as I wrote here, with the only exception that here instead of Z on the RHS I have Z inverse. Okay, rest of the things are the same. So this is nothing but my capital X of Z inverse, right? So x of minus n will have, I mean small x of minus n, which is the time reversed discrete time signal, will have a Z transform which is given by capital X of Z inverse. Okay, and now for the sake of completeness, we will also accordingly study its ROC. So okay, for x of z, for capital X of z, we took the assumption that the ROC is, let's say, bounded between R1 and R2. So mod z is lying between R1 and R2. So for x of for x of z inverse also, we need this to be satisfied. So mod of z inverse should be within R1 to R2. Okay, so that means that R1 less than 1 by mod z less than R2, and now this becomes 1 by R2 less than mod z less than 1 by R1. Okay, so this is now your new region of convergence. Okay, this is the change which happens in the ROC. So what we observed is that if x of n has z transform capital X of z with the ROC being bounded between small r1 and small r2, then x of minus n will have the z transform capital X of z inverse. Okay, and your ROC will be bounded within the reciprocals of those corner points of the previous ROC. Okay, the boundary points. So this is just one important property that we have seen in this example through the derivation. Okay, so ultimately x of z inverse is the right answer, so it is option A. Okay, now moving on to the third question. Okay, fine. All right, so in the third question, we are given that, okay, it's also a similar question to that of question 2. So it's given that if the z transform of a discrete time signal x of n is capital X of z, then the z transform of 4 power n 4 raised to the power n times of x of n is what? Okay, so again we are doing some modifications on the input discrete time signal, time domain signal, and we have to find the corresponding change that happens in its z transform. Okay, so x of n is capital X of z, and so I'm not again you can for the sake of completeness you can, okay, maybe I'll do that. I'll assume that it has some ROC, let's say, again given by this. And consider that like both r1 and r2 are non-negative. I mean they are yeah, they are non-negative and they are greater than 0, let's say, because they cannot be 0. If they are 0, then you see that in the previous example also we can't really take their reciprocals, because the reciprocal of 0 becomes undefined. So that's why I need that assumption. So let's keep that assumption. And my question is, 4 raised to the power n into x of n will have the Z transform, and that we need to find. Okay, so x of z I know again from the formula, and this is given by this. Okay, now let us find the Z transform of 4 raised to the power n into x of n. So it will be n running from minus infinity to plus infinity, 4 raised to the power n into x of n times z to the power minus n. So this is summation n running from minus infinity to plus infinity x of n. I can group these two terms here because they have this power n as common, you know. So I can group this 4 to the power n and z to the power minus n terms together and write this as z by 4 whole to the power n, right? Oh, sorry, z by 4 whole to the power minus n, right? Because that will give you 4 to the power n times z to the power minus n. Okay, yeah. So now you see this is in the same form. These two are in the almost same form, with the only exception being that here I have z by 4 instead of z. Okay, so this summation here is nothing but x of z by 4. So which is capital X of some 0.25 z. So option D is the right answer, x of 0.25 z. And let us complete this with respect to ROC as well. So we knew that okay, my mod z is lying between R1 and R2 for my original case, right? For this, yeah, original x of z. So for x of z by 4, for x of z by 4, which is in the new ROC, uh, this should also lie between R1 and R2 for it to be defined. Okay, so that means mod z lies between 4R1 and 4R2. That's the corresponding change on the region of convergence. So the complete picture is that x of n as, let's say, a z transform x of z with ROC as R1 bounded between R1 and R2, then 4 to the power n into x of n will have the ROC given by capital X of 0.25 into z and the ROC will actually uh, be bounded between 4R1 and 4R2. So in our options we are not given the knowledge of ROC. That was just for the sake of completeness I mentioned, but yeah, we are only concerned about the form of x of z. So that is x of 0.25z, which is option D. So the correct answer is option D. Okay, now let's look at the fourth question. Okay, so here we are given a figure 1, as you can see in question 4. We are asked to determine the nature of the system with respect to causality and stability. Okay, so four options are given: causal and stable, causal and unstable, non-causal and stable, non-causal and unstable. So which of these combinations is the right one for this system is what you need to determine. Given this knowledge of the ROC, okay, we have the region of convergence, as you can see highlighted in green shaded region, and which is lying to the exterior of this dashed circle, as you can see. And we have a unit circle as well, which is the smaller circle that I have drawn, that is enclosed within the dashed circle. And we have the two poles which are like the complex conjugates of each other. Okay, one pole at 1.5 plus j times 1.5, and another pole at 1.5 minus j 1.5. Okay, so they are complex conjugates of each other, as you can see, and they are marked in orange color. Okay, and here also we have this notation sigma for the real part of z, and j omega is the imaginary axis. So as I was saying, that this is also another notation. Okay, so for this given ROC, from this given figure 1, you have to decide which of the following options is true. So in order to comment about causality and stability of the system by looking at the ROC, you need to know the properties again. Okay, you have to go back. So let me first write those down. Okay, so this is question number 4. First let me redraw the figure. Okay, so sigma is the real part, j omega is the imaginary axis, and let's say somewhere here, and yeah, so we have the unit circle. So something like this. Okay, it's not drawn to scale, but yeah, you can understand. So this is the unit circle means it's a circle of radius unity, radius 1, and this is in z domain. Okay, so this is z domain. We are in the z plane where z is some complex number. Okay, so in this unit circle you can very well guess that any point will be of the form some e power j theta. Okay, because the absolute value of e power j theta is unit is 1, so it will always lie on that unit circle in the complex z plane. Okay, and if you want to actually write in terms of coordinates, it will be like you can specify any coordinate in terms of cos theta comma sin theta, okay, along this unit circle. So fine, now we have another circle which is outside this unit circle, whose radius is even more greater, this dashed circle, like this. And now we are given two pole locations as well. One pole is somewhere here, okay, which is at 1.5 plus j into 1.5. So this j is like the square root of -1, which is iota, right? Somewhere it's also denoted by small I, but here we are denoting it by small j. Okay, so 1.5 units on the real axis and 1.5 units along the imaginary axis. Okay, and another pole is also located at its symmetrically opposite point, so which is at 1.5 minus j into 1.5. So they are the complex conjugates of each other, these two poles. And finally, my ROC is this shaded region in green color, which is actually to the exterior of this dashed circle. Okay, like this. So this green region is my ROC, okay, which is the region of convergence. Okay. Given this ROC, I have to decide if my system is causal, if my system is stable or not. So before that, let us okay, I don't have much space here, but still let me write it here itself. Okay, let us remind ourselves with the properties. Okay, so for a causal system, point number 1, for a causal system, the condition for the ROC is that the ROC should lie outside of certain circle. Okay, so the ROC is outside of a certain circle, so it lies to the exterior of certain circle. So that's the condition for the ROC of a causal system. So that's regarding causality. And regarding stability, stable system, For a stable system, the ROC must contain the unit circle. Okay, so the unit, or in other words, the unit circle should lie within the ROC. ROC must contain the unit circle. Okay, and all this discussion is happening in the Z domain. Okay, because we are discussing Z transform, so these are all applicable in Z plane. Okay, not in S plane or anything. Okay, okay, fine. So this covers causality, stability, and you can actually combine them as a third case, which is like causal and stable system. And for such a system which is both causal and stable, one remark that you can claim is that all poles must be strictly inside the unit circle. Okay, so let me mention that as well. For both causal and stable system, all poles must be strictly inside the unit circle. Okay, and this actually you can combine both causality and stability condition to arrive at this condition, because you see that you also have to keep in mind that the ROC, for a valid ROC, it should not contain any poles. So that if you keep in mind, and for individually causality and stability of a system, you need these conditions, that ROC should be outside of a circle and it must also contain the unit circle. So if you combine all these conditions together, you can actually claim that okay, all poles must be strictly inside the unit circle. Then only I'll be able to ensure that the ROC will not contain any of the poles. So that satisfies my valid ROC condition, and also ROC will be outside of a certain circle, and also the ROC will be containing the unit circle. Okay, so it's like that. Okay, so now let us verify the causality and stability for this given system. So here, first of all, just by looking at the diagram, we can see that this green shaded region of ROC, that is lying outside of this circle, right, of the dashed circle. So the ROC is outside of a certain circle, which straight away tells us that it is going to be a causal system. So first observation is that here the ROC is exterior of the dashed circle, which means system is causal first of all. And what about the stability? So you can see that the ROC, which is the green shaded region, is not containing the unit circle, right? They are disjoint, right? So also the ROC does not contain the unit circle, which means that it is not stable, so unstable. So it is causal and unstable system. This is the right combination. There is also, I mean, uh, another case which is like marginally stable, but that is not true here because the poles are here strictly outside the unit circle, as you can see. For stability and causality, they need to be strictly inside the unit circle. Okay, if they were just at the boundary of the unit circle, then we could have gone for that case, which is marginal stability, but here it's not the case. So it's an unstable system, but it is causal. So the correct option is causal and unstable, which is option B. Option B. Okay. Now let's move to the next question. Yeah. So question number 5. Read the question. Okay, so this question is based on the initial value theorem of Z transform. Okay, I hope this has been covered in the lectures. Even if it's not covered, then also uh, we can learn something new. So it's pretty straightforward. So I won't be going to the proof of the initial value theorem, but yeah, so I'll directly use this result and solve this numerical question. So what we need to find is that, okay, first of all, we are given the Z transform, the form of the Z transform, which is capital X of Z. So you have a discrete time signal which is small x of n. Its Z transform is given by capital X of Z, which has this given form, as you can see. Again, in the rational form is the ratio of two polynomials of Z. The numerator polynomial is z square plus z plus 1, which is a second degree polynomial, and the denominator is also a second degree polynomial, which is clearly factorized into two first degree polynomials. And what you need to figure out is the initial value of x of n, that is x of n evaluated at n equals to 0, or in other words x of 0. Okay, that's the initial value of x of n. So for that we need to know the initial value theorem of Z transform. So there are similar initial value theorem and final value theorem for the Laplace transform as well in the S domain. But here we are talking about the Z domain. Okay, the initial value theorem and final value theorem for the Z transform. So let me state the initial value theorem. Okay, so it states that x of 0, I mean small x of 0, that is the initial value of x of n. X of n evaluated at n equals to 0 times 0 is given by this limit z tends to infinity capital X of z. Okay, and there is one condition that needs to be satisfied here. This is for, okay, I mean this holds true here. X of n, the time domain signal or sequence, which we often use in the context of discrete time. So this discrete time sequence needs to be a causal sequence. Okay, and particularly we need to assume that x of n is 0 for n less than 0. So we'll assume that it starts at n equals to 0 and so on. So it's a causal sequence in that sense. So this is my statement. Okay, so given our question, which is x of z is given as z square plus z plus 1 whole divided by z plus 2 into z plus 1. Okay, this was the question. Yeah, so from the initial value theorem I can write that x of 0 will be given by limit z tends to infinity x of z, which is equal to limit z tends to infinity. I can replace x of z by the given form. This, okay, so now I can actually cancel out certain common factor from the numerator and denominator. I can actually cancel out z square, okay, from the numerator and denominator. So here this will be z tends to infinity. So if I take common as z square from the numerator, then in the numerator I'll be left with 1 plus 1 by z plus 1 by z square, right? And similarly from the denominator, what I'm going to do is I'm going to take z as common from each of the factor. Okay, so overall it becomes z square, and I have 1 plus 2 by z into 1 plus 1 by z. Fine. So these z square and z square gets cancelled, and now in my next step what I am going to do is that, so now I am in a form where I have terms as reciprocal of z, okay, 1 by z, z inverse, okay, all the terms are in that form. So if z tends to infinity, then 1 by z will tend to 0, okay. So I can write this as limit 1 by z tends to 0, and here I have 1 plus 1 by z plus 1 by z squared in the numerator, and in the denominator I have 1 plus 2 into 1 by z, that's the first term, and I have 1 plus 1 by z. And now I can actually substitute the limit, can directly put 1 by z equals to 0 here, okay. So I'll get 1 plus 0 plus 0 in the numerator, and 1 plus 0 here, and times 1 plus 0 again, that is basically 1, okay. So that's the limiting value of x of z as z tends to infinity, which is exactly my x of 0, small x of 0, the initial value of x of n. So the answer is 1. As an exercise, what you can do is, of course, you assume that it's a causal sequence x of n, and let's say x of n is 0 for all n less than 0. So you can actually, given this criteria of causal sequence, then you can actually find your x of n, the explicit form of x of n, either using inverse Z transform, or you can use some properties that we have looked so far, right, to go from x of z to x of n, and then you evaluate that x of n at n equals to 0 and check, verify whether you are getting 1 or not as the answer. So that's an exercise. Okay, now moving to the next question. Okay, okay, so this is the 6th question here. So now we will explore the final value theorem. Okay, we have seen the initial value theorem. Now this question is based on the final value theorem of Z transform. Using final value theorem, we have to calculate small x of infinity. Okay, if the Z transform x of z is given by this. Okay, again this is a rational, in the rational form. So let's see. So for that, let me first discuss the final value theorem. So it states that limit n tends to infinity x of n, which is basically your x of infinity, is given by limit z tends to 1, 1 minus z inverse times capital X of z. Okay, this is the initial value theorem statement, and again here x of n is causal. I'm not going into the proof of this. You can readily find these proofs in textbooks or any place. Okay, even online also. So here in our question, let's see what is x of z. So let me go back to the question. So we have z plus 1 divided by 3 into z minus 1 into z plus 0.4. So z plus 1 whole divided by 3 into z minus 1 into z plus 0.4. Okay, so let us now evaluate the final value, which is limit n tends to infinity x of n, which is actually x of infinity, given by limit z tends to 1 1 minus z inverse into x of z. So that is nothing but limit z tends to infinity, sorry, z tends to 1 1 minus z inverse into the given z transform. Okay, okay, so now I can rewrite this as, I can multiply both numerator and denominator by z. So what I am going to get is, so this 1 minus z inverse term here becomes z minus 1 if I multiply with z, and accordingly I will also have to multiply with z in the denominator. So I have 3 into z minus 1 into z plus 0.4, and clearly this z minus 1 and z minus 1 gets cancelled. So I'm left with, just a second, so I'm left with this part, z plus 1 whole divided by 3z into z plus 0.4, and now I can directly substitute the limit, which is limiting value, which is z equals to 1. That will give me 3 into 1 into 1 plus 0.4, which is 2 by 3 into, okay, so let's not just confuse this with 3.1 maybe. So this is simply, I'll directly write 3. Okay, 3 into 1, so this will be 3 into 1.4, which is 2 divided by 4.2, and it's equal to 0.4762. So your correct answer is, the final value of x of n, that is x of infinity, is 0.4672. So you can expect these kind of questions in numerical answer type questions, right, where you won't have any options. These are not MCQ questions. You have to just write the final answer, the numerical value. Maybe you can be asked to, round it off to certain decimal places. Okay, but yeah. So this is the initial value theorem as well as final value theorem. Okay. And again, first for completeness, you can actually uh, explicitly derive its inverse Z transform. Uh, you can obtain small x of n, the actual general form of x of n for question number 6, and then evaluate it at n equals to infinity. What happens to verify the initial value theorem? Okay. Now moving on to the seventh and final question for today. Okay, so here we are going to actually go from x of z to x of n, small x of n. Okay. Um, so it has been asked that using partial fraction expansion and the fact that, so this relation is given to you. This is a known result that a to the power n times u of n has a z transform given by 1 divided by 1 minus a into z inverse, with the ROC being given by mod z greater than mod of a. Okay, so this is a known result, and in fact we have seen this result in case of the DTFT, or let's say the Laplace transform and so on. So but this result is now given in the Z domain. Okay, using this result we have to determine the inverse Z transform of capital X of Z, which is given in this form, and the ROC is also given, which is mod Z greater than 2. Okay, so we have to derive small x of n, which is the time domain, discrete time domain signal. Okay. Okay, and it is already given that you have to use partial fraction expansion. Okay, so let's do this. Maybe I'll go to the next page. Okay. So our known result is that a power n into u of n has a z transform given by 1 divided by 1 minus a into z inverse, with the ROC given by mod z greater than mod a. Now in our question we are given that capital X of z has this form: 1 minus 1/3 z inverse whole divided by 1 minus z inverse into 1 plus 2 into z inverse, and the ROC for this z transform is given by mod z greater than 2. Okay, and following our standard notations, we have this z transform pair, which is like x of n goes to capital X of z on taking its z transform, and like you can go back to x of n by taking the inverse z transform of capital X of z. Okay, so these two are the z transform pairs, and in our question we need to find this x of n, small x of n, the time domain signal. And for this we first of all have to use this known result which I stated in the beginning, and also use the partial fraction expansion. So for these kind of forms of x of z, here we have some linear term in the numerator, and we have product of two linear factors in the denominator. So in these kind of forms, there is, I mean, depending on the form of the transfer function, you have to follow the rule of the partial fractions. So here you can actually express this as, so let me write it. So let your x of z, which is actually 1 minus 1/3 z inverse whole divided by 1 minus z inverse into 1 plus 2 z inverse, this be equal to some a. Okay, a is some constant, we don't know, can be real, can be imaginary, we don't know. Okay, it's a complex number in general, complex constant a divided by the first factor in the denominator, which is 1 minus z inverse, plus some other constant, complex constant b, divided by the second factor in the denominator, which is 1 plus 2 z inverse. Okay, this is how we can use partial fraction for such a form and decompose this into sum of two such terms, okay, as I wrote here. And then we will make some substitutions and all to find this a and b. The purpose of writing this in this a by 1 minus z inverse plus b by 1 plus 2 z inverse form is that once we figure out what the value of a and b are, then my x of z will be exactly in the desired form, right? Because I know that 1 by 1 minus a into z inverse, this z transform has an inverse z transform given by a raised to the power n into u of n. So if I am able to express this in this a and b form here, then I can straight away use that given result and property to go back to x of n directly, right? So that is why I am using this partial fractions here. Okay, and note that here I am able to express this in this a by one factor plus b by another factor because of the given form. Okay, if there is some other form of the z transform, then you have to express that in some other form. Okay, so but I am not discussing every form here. You can find that in any reference book or anywhere online. Okay, so suppose this is the case, then I also need to find what a and b are. Okay, so this means that my a into, so here if I compare the numerators on both sides, LHS and RHS, what can I say? A into 1 plus 2 into z inverse plus b into 1 minus z inverse is equal to 1 minus 1/3 into z inverse. Okay, now how do we find a and b? So I have an identity here. Okay, so in order to find a, let's put z equals to 1 in the above identity. Put z equals to 1, z equals to 1. So how that helps is that my coefficient of this b term, the second term here, becomes 1 minus z inverse. So z, if I put as z equals to 1, then this factor becomes 0 actually. So I'll be left with a into 1 plus 2 z inverse, so which is a into 1 plus 2 into 1, so that is 3a, and this will vanish, is equal to, on the RHS I will have 2/3, which gives me a equals to 2 by 9. Okay, And similarly to find b, I can put some substitution, I can make a substitution for z such that my uh, a term vanishes. So for that I'll substitute z equals to -2. Okay, because if I substitute z equals to -2, then the coefficient of a in the identity becomes 1 plus 2 into z inverse, which is 1 plus 2 into minus half, which is 0. And I'll be left with, so this part will be 3b by 2, you can check, is equal to, on the RHS I will have 7 by 6, and that will give me b equal to 7 by 9. Okay, so now I have expressed x of z in the desired form. So now x of z is equal to, what was the form, a by 1 minus z inverse. So I just figured out a, which is 2 by 9 into 1 minus z inverse, plus b by 1 plus 2 z inverse, where b is 7 by 9. 7 by 9 into 1 by 1 plus 2 z inverse. Now I can simply, take its inverse z transform, because I already know this result, right? That 1 by 1 minus a z inverse will have an inverse z transform a raised to the power n u of n. So if you take its inverse z transform, you will get, so here compared, first let's do term by term, because we will be using linearity, right? So for the first term here, okay, we have 2 by 9 as a constant factor outside, so that stays. So here 1 by 1 minus z inverse. So here that a term is actually equal to 1. So 1 minus, so 1 by 1 minus z inverse. This has basically, so here a term is 1. If you compare with that form, 1 by 1 minus a z inverse, this a term is 1 here. So this will have basically a to the power n u of n becomes 1 to the power n u of n, which is simply u of n, right? And what about the other term, 1 by 1 plus 2 into z inverse? So that will be, that will have a z transform, inverse z transform given by, so here my a is -2 basically, if you compare with that 1 by 1 minus a into z inverse form. So this will give you -2 to the power n into u of n as its inverse z transform. Okay, all right, so now, and for the sake of completeness, let me also specify the ROC. So for this part here, my ROC should be mod z greater than mod a, right? Mod z greater than mod a. So for this part should be mod z greater than 1. Okay, because a is 1 here. And for the second part, I also need mod z greater than, here for the second part my a was -1, sorry, -2, so its modulus will be 2, so like this. And since I am using linearity and I have a combination of these two cases, so I have to take the intersection of these two ROCs for the overall part. Okay, so combining these two, my ROC is basically mod z greater than 1 intersection mod z greater than 2, which gives me basically their intersection is basically mod z greater than 2. So I have 2 by 9 u of n plus 7 by 9 into minus 2 to the power n into u of n, and my ROC is mod z greater than 2. Okay, so this is my final result. Okay, yeah, and it was already given, the ROC was already given in the question, that mod z greater than 2, and by using partial fraction also we actually uh, verified that indeed, yeah, that ROC is satisfied. Okay, so yeah, so yeah, I think we have covered all the questions. So with this, we have come to the end of all the live sessions. So um, hopefully it has been helpful so far for solving the assignments and also for the final exam. You can drop me any queries via email, anything. I'll be happy to help. Or you can also discuss your doubts in the discussion forum of the course webpage. Uh, so okay, so I'll stop for today, and yeah, so that's the end of the live sessions, and maybe in the future we'll meet for some other course or something like that. So all the best to all of you. So thank you.